Example 23, a distributed loading of P is equal to 800x pascals acts over the top surface of the beam shown in the figure. Determine the magnitude and location of the equivalent resultant force. Okay, now if you can observe, we are given a unit of pressure, so that's Newton per meter squared. But if we can look at our image here, the width of our structure is constant over the entire length, which is 9 meters, and the width is 0.2. So therefore, what we can do is that we can express our distributed loading as uh, in units of Newton per meter so that we can view it as two-dimensional. Because like I said, the width over the entire length is equal. So what we can do is that F, so F or our distributed load, let us use W. Our this W is equal to P times your width. Let us call width as B. Okay, so this becomes 800x times our width, which is 0.2 meters. And we know 800x as a unit of Newton per meter squared. So Newton per meter squared times meter, it becomes Newton per meter. So our distributed loading now becomes 800 times 0.2, that's 160x. And the unit is in Newton meter. Now, if you can observe, it is also provided that at the edge of our loading, at 9 meters measured from here, 9, the load is 7,200 Pascal. So what we can do is we can also say that at x is equal to 9 meters, can do would be load is equal to 7,200. Still multiply it with our width, and that is times 0.2. So our W at 9 meters is 7,200 times 0.2 becomes 1,440 Newton per meter. Now, if you want, we can also say using this equation, which is W is equal to 160x, or x is equal to 9 meters, W, which is equal to 160x. So if you can observe, this is a linear equation. So is equal to 160 times 9, because our x is 9. W is 160 times 9 is still 1,440 Newton per meter. So now we can view our distributed loading as two dimension. So it becomes, this is uniformly varying. And this part here is fixed, right? So we have arrows going down. And until here, the very last part is 1,440 Newton per meter, and the entire length is 9 meters. Now, we are given two options. I will be showing you guys two solutions, but it's up to you on what solution to use. Okay, but first solution would be I will be using the integration, right? Because again, we are provided W is equal to 160x as our uniformly distributed, uniformly varying load. So like what we did in our previous example, we can take a strip here, somewhere here, and this is our dA, which is equal to W dx, right? Okay. And then this becomes uh, F sub R is equal to the sum of all forces in the Y. Now I don't have to assume any the direction of our resultant force because there is no other force present other than all the distributed loading going down, right? But it's up to you nga if butang pa ba mo assuming upward positive when in fact wala naman siya lain pang makita, right? Okay, this is equal to uh this is also equal to A, but since we don't have a fixed A, what we can do is that we do integration, differential, integration of A, and we know this is uh W dx, and our W is 160x dx. And of course, we will integrate that over our entire length, which is 9. So from 0 to 9, this is equal to 160 from 0 to 9 x dx. So this becomes 160 times x squared over 2 from 0 to 9. So of course, at 0, it becomes 0. So diretso lang ta sa 9. So this becomes 160 times 81 x squared. 9 squared is 81. So 81 divided by 2. And then our f sub r is equal to 160 times 81 divided by 2 is 6,480 Newton. That's our resultant. Okay, for our, this is magnitude, solution A, magnitude. Okay, we have location. So this is x, bar x is equal to the integral of x dA over dA. And we have calculated dA already. So this becomes, dA is 6,480, right? But of course, our dA here, we just rewrite this one as x w dx over the integral of dA. Oh, wait, let me rewrite dA as well to w dx. We already did w dx at the bottom, and that is 6,480. So we substitute all of our values. So w dx, this is what integral of x times 160x dx divided by 6,480, right? Because again, we are still evaluating it from 0 to 9. 0 to 9. This is 160 integral from 0 to 9 of x squared dx divided by 6,480. And this is equal to 160 over 6,480 bracket, that is x cubed over 3, evaluate it from 0 to 9. So again, I will not include 0 because 0 ramang gud siya gihapon. This is then equal to 160 divided by 6480 bracket 9 cube divided by 3, and our bar x is equal to 9 cube is 729 divided by 3. That's 243 times 160 is 38,880 divided by 6480, and that is 6 meters from the tip. So when I say from the tip, this tip, this is tip. Okay, so this is our what do you call that? Our location of our, what do you call this? Our resultant force. Now for solution number two, uh, option two or solution B, if we can observe, our loading is uniformly varying, right? And it creates a triangle. And we know that at the edge here, we have W is equal to 1 4 40, I believe, 1 4 40, right? Newton meter. Newton per meter. Okay. So what we can do is that, since given that our uh, structure, our loading is uniformly varying, and it follows it takes of a shape of a triangle. So, and by definition of our F sub r, we're in that our F sub r is equal to the area of the loading. So we can just use the area of our triangle to find for our uh for resultant force, right? Wherein our height would be the at the back portion of our uh, triangle, which is 1 for 40 Newton per meter, and then the base would be the entire distance, which is 9 meters. So this becomes now F sub r is, and the area of our triangle is 1/2 base times height. Now our base is 1/2 times our base, like I said, is our 9 meters times our height, which is 1 for 40 Newton per meter. So you have base times height, that's meter times Newton per meter is Newton, right? So our F sub r is equal to 1 for 40 times 9 is 12,960 divided by 2 is 6,480 Newton, which is the same with the value we got using integration. Now for our location, we will be using, since like I said, is our loading follows a uniform shape. The loading follows a regular shape, which is a triangle, and the centroid of our triangle is calculated as, which is will be provided in our Google Classroom to be, say this is our resultant force x here, F sub r. It is measured 2/3 from the tip and 1/3 from the back. 1/3 from the back. So therefore, x location, now this is magnitude, and for our location, that is bar x is equal to, if you want to measure it from the tip, so that is 2/3 times our length, which is 9. So x prime is equal to 6. 2 times 9 is 18, divide 3 is 6. This is 6 meters from the tip. If you want, you can also measure it from the back end. So you just have to multiply 9 with 1/3. So the resulting x would be 3 meters from the back. Okay, so yeah, we are presented with two options on how we are going to solve for the magnitude and our location of the equivalent resultant force of our distributed loading.